Today we're going to see how functions other than the mother function of a quadratic function can be transformed. So starting with number 1, we're going to graph the function f of x equals x squared minus 2x minus 3. You can see on my calculator that I already have it pulled up. So if you want to go ahead and get there, you go to y equals, type in your function rule. F of x is the same as y, x squared minus 2x minus 3. Pull up your table. Now, when you've got your table up with any quadratic function, you're looking for the turning point or the vertex of the function. So you want to be able to make sure you're graphing that point so you're proving that you understand that a quadratic function is that U shape. So I have in my window the vertex right here, 1, -4. Since all the other points on the y-axis are more than -4, that proves to us that this is going to be a minimum point. I know that, though, just by looking at my function rule. I know that the x squared term is positive, therefore this function is going to go up and have a minimum point. So taking a look at these points, we can go ahead and graph, starting with -3, 12. -2, 5. -1, 0. 0, -3. 1, -4. 2, -3. 3, 0. 4, 5. And 5, 21, and 5, 12, not 5, 21 rather. Here I see I have my true U form and a minimum point. I'm going to neatly draw my line through my points. With arrows on both ends, since I wasn't given a specific domain to graph it over. So in this case, I know I can point out a couple things just to remind you. Here I have the roots. So this point right here and this point right here are the roots of my equation. They're at -1 and +3. I can even see that on my table, 3, 0 and -1, 0 were my roots. I have my vertex, which is a minimum point at 1, -4, and it's a positive function because it's going up. So I really should label this equation as well, since we're going to graph two equations on the same line or on the same coordinate plane. So I'm going to label this one f of x. So now I have g of x is equal to f of x plus 3. So determine the function rule for g of x to determine and graph it on the same grid. How did the graph of f of x change to get g of x? So whenever you have something like this, you just take the function f of x that they originally gave you and replace it in the second function g of x. So for number 2, we're going to rewrite g of x equals the function rule for f of x, which is x squared minus 2x minus 3, all plus 3. Now, I could simplify this one because it's not so hard to simplify. This is going to be g of x equals x squared minus 2x because the positive 3 and -3 cancel out. So now we're going to go ahead and graph that on the same coordinate plane and see what happens. So we go back to our y equals. I'm just going to go ahead and delete the -3. Then pulled my table back up. Now I see that my vertex is at 1, -1 instead of before where it was at 1, -3. I'm going to go ahead and graph some of my points. I can't go as high as 15, so I'm going to start at that -2, 8, -2, +8, 1, 2, 3, 4, 5, 6, 7, 8. Then -1, 3. Then 0, 0. Then 1, -1. 2, 0. 3, 3. Four, 8. I'm going to go ahead and graph that line as well. With arrows on both ends and label it g of x. So we can see something that clearly happened between f of x and g of x. Now, my graphs aren't so neat, but they should have the same shape. My blue one looks a little bit off. But you should notice that all g of x did to f of x was shift it all up 3 units because it affected the k value of the equation. If you remember back in that standard or the vertex form of the quadratic function, the k shifted the function up or down. So in this case, that plus 3 is like the k value, so it shifted our f of x function up 3. Okay, taking a look at number 3, we're going to do something very similar. Starting with the graph f of x equals negative 2x squared plus 8. So we go to y equals, clear our equation, go to negative 2x squared plus 8, and pull up the table. And here we see our vertex right away at 0, 8, which in this case is a maximum point because our a value is negative. That proves that the graph has to go down, so our vertex has to be a maximum. So we can go ahead and graph those couple points there. We have negative 3, negative 10, negative 2, 0, negative 1, 6, 0, 8, 1, 6, 2, 0, and 3, negative 10. So in this case, we see a very narrow quadratic function or parabola because of the negative 2 out front. It's also reflected and upside down because of the negative. We neatly draw our line and label it f of x. So now we're going to see how h of x affects this new f of x. So in this case, it says h of x equals negative 1/2 of f of x. I know your equation is a little bit different. Go ahead and subtract or cancel out the plus 2x that's there. We're going to remove that from today's example. So all we have to do here is, again, replace our f of x with the f of x in the h of x equation. So we have h of x equals negative 1/2 of negative 2x squared plus 8. And there's no need to rewrite it. You can simply put it into your calculator exactly that way, and it will do the changes for you. So we can go to our y equals, clear what's there, put in negative 1/2, then another set of parentheses, negative 2x squared, plus 8, close the parentheses, pull up the table. So now we see we have a minimum point instead of a maximum point, which makes sense because the negative and a negative is going to make this a positive, so it's going to reflect our original equation. Okay, so we're going to start graphing this and then say what happened here. So we have 0, negative 4, or I'm going to start up at the negative 3, 5. Let's see, I can also do negative 4, 12. No, I can't. So negative 3, positive 5. Negative 2, 0. So the roots are the same. Negative 1, negative 3. 0, -4, 1, -3, 2, 0, and then obviously the next point would be symmetric to this one, so 3, 5 as well. Go ahead and graph your function. Arrows on both ends, and label it h of x. And now we can answer this question. How did the graph of f of x change to get h of x? Well, it was reflected over the x-axis and compressed by 1/2, which is stated within what h of x tells us. The negative sign tells us that it is a reflection. The 1/2 tells us that this is going to be compressed, which also makes sense because the vertex here was at 8. Here it's at 4. Half of 8 is 4, so that's being shortened as well. So it's something we can think about. All the other points were also cut in half. If you looked at all the y values, they'd be half of what they originally were, but upside down. Okay, so we have one more to do. Starting with number 5, we're going to graph the function f of x equals x squared minus 6x plus 5. Just by looking at that function, you guys should notice right away that it has a minimum vertex because the a value in front of the x squared term, which there isn't any a value, but that shows us that it's a positive function, so it has to go up and therefore has a minimum value. So we go to our y equals, we clear what's there, we graph x squared minus 6x plus 5, pull up our table, and there are points again, and I know it looks like the same type of points over and over again. They're just all over the coordinate plane, just because it's the type of functions that I chose to make it work and make it graph nicely for you guys for these ones. So we have -112, then 0, 5, then 0, 5. Sorry, I realized I messed that one up, so I was just fixing that. Then 1, 0, then 2, -3, 3, -4, 4, -3, 5, 0. There are roots at +1 and +5. 6, 5, and 7, 12. Then neatly draw your line through your points. Arrows on each end. Label it with the function f of x. So now this last one is the trickiest of all of them. We have f of x plus 3, q of x equals f of x plus 3. So whenever we have that f of x plus 3, something with parentheses around what the transformation is asking us to do, that means it's going to replace every x value. Every x is going to change to x plus 3. So when we go ahead and rewrite this, we have to be very careful that we don't mess anything up. And we go slow and fill it in. So this part replaces all the x's in f of x. So q of x equals x plus 3 squared minus 6x plus 3 plus 5. And again, we can enter it into our calculator exactly that way. So we don't have to do a lot of math here to write the equation in standard form unless we're told we have to put it in standard form. And in that case, we would have to do out the x plus 3 all squared and distribute the 6. So we have y equals, parentheses, x plus 3 all squared minus 6 times x plus 3 plus 5, and pull up our table. Looks like I have to go up, and I definitely do. And I can see, again, those same points, but different x values attached to the y values. So we're going to start by graphing -4, positive 12. Then -3, positive 5. Then -2, 0. And hopefully you're already seeing what happened here. Then -1, -3. 0, -4. 1, -3. 2, 0. So in this case, the roots are at positive 2 and -2. 3, 5. And 4, 12. Go ahead and draw your line neatly. Much neater than mine, hopefully. Arrows on each end, and label it Q of x. So hopefully you see here that the blue f of x was shifted 3 units to the left to get Q of x. So this x plus 3, like we saw in vertex form, is a shift 3 units to the left. Okay, so we would say, how did the graph of f of x change to get h of x? It is a shift 3 units to the left to get h of x. So you're going to go ahead and answer your ISA tickets and then start your homework. Tomorrow you'll be working on some of these problems within your group.